To put this lecture in context, I want to bring you back to our result for the total response of a linear system. If you remember, the total response was the output of the system due to both initial conditions and also the input. Recall that for linear systems, the total response was the summation of the zero input response and the zero state response. The zero input response is the response to initial conditions, and the zero state response is the response to the input. And we can simply sum those together, superposition, and find the total response of the system. Today we're going to talk about the impulse response, and the impulse response is very important in finding the zero state response. We introduced the impulse or Dirac delta function earlier. Now we're going to look at why the impulse response of a system is so important. The impulse response of a system is the output of the system when the input is an impulse. And today I'm just going to sketch out why this is important to system response. We'll cover this in much greater detail in a later presentation. So why is the impulse response so important? The reason why is because it helps us find the response to an arbitrary input. The way it does this is by using the properties of linearity and time invariance. Let's suppose we can find the response to a pulse of height 1 and width delta t. This is shown in the bottom left. And let's suppose that response is yp of t, shown in the right. Let's now consider how to find the response to the input x of t equals 2p of t plus 3p of t minus cap t. That's the signal shown here. Now we can use the superposition and time invariance properties of our LTIC system to find the response to this input. We'll label this response y of t, and it can be found as follows. Y of t equals 2yp of t plus 3yp of t minus cap t. Why is this so? Well, the response to p of t is yp of t. The response to 2 times p of t is 2 times yp of t by homogeneity. The response to p of t minus delta t is y of p of t minus delta t. The response to 3 times p of t minus delta t is 3 times yp of t minus delta t. All of this by time invariance and superposition. So what have we done? We've taken our input x of t and we've broken it up into 2 parts. One part is 2 times p of t. The other part is 3 times p of t minus delta t. Since we know the response to p of t, we can use superposition and time invariance to find the response to this signal. And that response is 2 times yp of t, which is the response to 2 times p of t, plus 3 times yp of t minus delta t, which is the response to 3 times p of t minus delta t. I hope you see the fundamental idea here. And if you understand that, you can understand the following: that we could apply the same idea to find the response to an arbitrary input, x of t. We break up x of t into a series of pulses of different heights. The heights correspond to the values of x at these individual times. And then we compose a signal from these heights and pulses which have been delayed in the following fashion. X of t equals a summation over index I of xi p of t minus I delta t, where I indicates which pulse we're referring to. And then in response to this input, we get the output, which of y of t equals summation over the indices of xi times yp of t minus I delta t. You see the response to p of t is yp of t, and so the response of p of t minus I delta t is yp of t minus I delta t. Then all we need to do is to adjust for the value of the strength of each pulse, which is given by the height xi. We have only approximated x of t. X of t might be smooth, but we've approximated by a series of rectangular pulses. So of course the answer we're finding here for y of t is the response to this non-smooth x of t. So this brings up the question of how do we find the response, the true response, to the real x of t? And the answer is what we need to do is to make the rectangles thinner and thinner, and by doing so we get more and more accurate approximation. And as delta t goes to 0, the number of rectangular pulses will go to infinity, and the approximation will become perfectly accurate. So that's our next step in trying to understand this, and this is the basis of the convolution integral itself. So here's the last piece of this idea. As delta t goes to 0, the pulses will become infinitely thin and will become like impulses. So I think you can see now why the impulse response is so important to us. So to summarize, the key to finding the response to an arbitrary input is to find the response to an impulse. This material is the background for the convolution integral, and the convolution integral, which we'll cover shortly, is one of the most important topics in the class. You should make sure that you understand this material so that you're well prepared to tackle the convolution integral.